Good afternoon, children, and I welcome you all to lecture 5 on chemical bonding. Let us begin. So last class we had just started with hybridization. Today we'll be continuing again from hybridization and we'll see what happens in hybridization and how it's done. Although I've already told you that what is hybridization and what are the tricks for hybridization. Okay. So basically, what is hybridization, children? So hybridization is the intermixing of orbitals, right? Hybridization is the intermixing of orbitals where you mix the orbitals which are having similar energy or which vary in their energy slightly. Okay, that is called as the hybridization, right? Okay, so we are having atomic orbitals. Okay, suppose there is one atomic orbital and there is another atomic orbital. These two atomic orbitals having similar energy. Okay, they're having similar energy. Now, when they combine, they are going to give you hybrid orbitals. They're going to give you hybrid orbitals. And this process is called as hybridization. This process is called as hybridization. Now, when these hybrid orbitals are formed, suppose n number of hybrid orbitals are formed, then all the hybrid orbitals are going to have equivalent energy and shape. Okay, equivalent energy and shape. Suppose one of you is square shaped, other is square shaped, and you give rise to what? A hybrid orbital which is circular in shape. So how many circles will be formed? They will all be having the same energy and the same shape. Okay. So what is being told here? Let us see the definition. Hybridization can be defined as a process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of a new set of orbitals of equivalent energies and shape. Okay, so that is the hybridization. I hope you all are clear with the definition. Then what is essential is the main features of the hybridization. So what are the main features of hybridization that we are going to see? This part is important. It is being told here that the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. That means, suppose you are combining one atomic orbital with another atomic orbital. So total of 2 orbitals you are combining. So you are going to get 2 hybrid orbitals. You are going to get 2 hybrid orbitals. So the total number of atomic orbitals that you combine is equal to the total number of hybrid orbitals that you are going to get. Yes. So the number of hybrid orbital is equal to the number of atomic orbital that gets hybridized. Okay. So this is your first thing. What is the second thing? As I told you, if this is looking square in shape, this is also going to look square in shape. That is just for assumption that they are not square in shape. Okay. So they're always equivalent. So if this energy is E1, then this energy is also going to be E1 and their shapes are also equivalent. Energy is also equivalent. Yes, this is the second point. So the hybridized orbitals are always equivalent in energy and in shape. This is the second point. Let us move on to the third one. The third one says that, I'll read out the points and I'll explain to you. They are more effective in stable bonds. Okay, so we saw that in VVT, the atomic orbitals were forming bonds. Okay, then why did we make MOs? Why did we make molecular? Why did we make hybrid orbitals? Okay, why did we make hybrid orbitals, children? Because they are more stable bond formation. They are exhibiting more stable bond formation. Okay, so the hybrid orbitals have more stable bonds than the pure atomic orbitals. Okay, this is one thing. Then we know that the molecules that have covalent bonds, they have some shape, right? They have some shape. So we are saying that the orbitals which are there, they are arranged or oriented in a certain direction in the space. Okay, and why are they oriented in certain direction in space? So that your repulsion is minimum. Your repulsion is minimum. Yes, that is the reason. Okay, and distance is such that the distance is maximum and the repulsion is minimum. Okay, So these hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of a molecule. This part is important. Like we know that if it is sp3, then it should look like tetrahedral. I have given you. If it is sp2, it should look planar. But when the lone pair comes in, like sp3 in ammonia, it's having one lone pair, so the shape is not tetrahedral anymore, it becomes pyramidal. Yes or no, children? So we know that when lone pairs are coming, somehow the orbitals are getting arranged in such a way that the repulsion is minimum, and they are arranged in such a manner such that the geometry is having a stable arrangement. Okay. Now, there are certain important conditions for hybridization. What are they? Let us see. So, the first condition is that only those electrons that are present in the valence shell, they are getting hybridized. Okay. So, this is the valence shell electron and they are getting hybridized. Okay. Note down all these points, children. So what's happening, children? You have to take care that only the orbitals that are present in the valence shell, they are getting hybridized. Yes. Okay. For example, if I tell you one is 5p here and another is 4s here. Just a minute. So let us take for carbon. Carbon is 1s2, 2s2, 2p, 2, right? 6 is the atomic number. So this is not going to take part in hybridization. Only the last shell. Okay, the last shell is n equals to 2. N equals to 2. Only this is going to take part in your hybridization. Okay, so what is the first rule? The first rule says that the orbitals present in the valence shell of the atom are going to be hybridized. Yes. Okay. And those orbitals which are undergoing hybridization, they should have almost same energy or very little difference in energy. So the second point, orbitals undergoing hybridization should have almost equal energy. Yes. Then last we saw in VVT. What did we see in VVT, children? We saw in VVT that only unpaired electrons were able to form bonds, right? Okay, they could only be forming bonds, but here the promotion of electron is not necessary or essential condition prior to hybridization. Okay, it is not necessary only half filled orbitals participate in hybridization. In some case even filled orbitals participate in hybridization. So in VVT it was saying you should have an unpaired electron, but your hybridization is saying it can have paired electrons and still it can undergo hybridization in some cases. Okay, so these are the 3 to 4 points that you need to remember. Okay. Yes. So first of all, valence shell, equal energy, promotion is not necessary, and even full filled orbitals can take, or the filled orbitals can take part in your hybridization. Yes. Okay. Now we will see the major or three major types of hybridization that we have is your sp, sp2 and sp3. Right, these are your three major types of hybridization that we are going to see. And in that case, the first type that we are going to see, children, is your sp hybridization. What hybridization? Sp hybridization. What happens in case of your sp hybridization, children? As we can see, one s is combining with one p, one s is combining with one p to give you sp hybrid orbitals. And how many sp hybrid orbitals are going to be formed? The number of atomic orbitals that we have taken. So we have taken one s and one p. So obviously we are going to get two sp. We are going to get two sp hybrid orbitals. Yes, children, we are going to get two sp hybrid orbitals. Yes, and how does the sp hybrid orbitals looks? That let us see that. Now we know that our s orbital is spherical in shape. We know that our p orbital is dumbbell shaped. Now when they combine, this is going to be your sp hybrid orbital. So one lobe is shorter like this and one lobe is bigger like this. So this is going to be your sp hybrid orbital. This is going to be your sp hybrid orbital. And here if we see now example, you can see example is your BeCl2. What we are going to see, children, BeCl2 is your example. So if we consider, like we know that the central metal atom, whenever we talk of hybridization, children, we are talking the hybridization of the central metal atom. That means here the central metal atom is beryllium. So hydrogen, helium, lithium, beryllium. So what is the atomic number? It is 4, right? So this is 1s2, 2s2, right? 1s2, 2s2. Then we talk about chlorine. So what, children? Chlorine. So if we want chlorine here, now you see this is 1s2, we'll make orbitals here. This is 1s, this is 2s. Now if we see the electrons here, this is 1 electron, this was 2 electrons, but now we need to make sp. So p is here, px, py, pz, any one you can take here. So this will be your 2 itself here and 1 will be promoted here. So this is 1 and there it's going to be 1 more. Here nothing is there. Okay. So you are going to combine this and you are going to get sp hybrid orbital. Yeah. And out of that you got here. So beryllium is having your sp hybrid orbital here. Okay. And now chlorine is coming and combining with it. Chlorine is combining and coming here and combining with it. So that's how you get your BeCl2. Right. Okay. So if you see in case of Cl, if I see in case of Cl, so Cl is having atomic number of 17, right? So 1s2, 2s2, 2p6 is 10, 3s2, 3p5. Yes. So if we see that 3s is there and 3p5, 1, 2, 3, 1, 2, 3, 4, 5. So one p orbital is there, no, children? One p orbital is there. So this is having one unpaired electron. This is having one unpaired electron. So now if we see, this is the sp hybrid orbital of beryllium. Yes. Okay. This is the sp hybrid orbital of beryllium. And from here, chlorine is having a p orbital. Yes. Now this p orbital is going to come. This p orbital is going to come and get combined here. This p orbital, this is of chlorine. Yes. This is the p orbital of chlorine. This is sp hybrid orbital of beryllium. And this is going to come and combine. Yes, understanding, children? So this is the sp hybridization and how it happened. Okay. Let us go ahead and see the next type of hybridization. The next type of hybridization that we are going to see, children, is your sp2 hybridization. What hybridization? sp2 hybridization. So as we can see from here, in sp2 we are having 1s and 2p, right? So total 3 atomic orbitals. Yes. So how many hybrid orbitals are we going to get? We are going to get 3 hybrid orbitals like this. 3 hybrid orbitals like this. This one is your sp2 hybrid orbital. Okay. As you all can see here, this is what we are going to get. This is known as planar shape. This is which shape, children? This is planar shape. If I tell you of an example, okay, if I tell you of an example, we can take BF3. We'll take the example of BF3. Boron is having the hydrogen, helium, lithium, beryllium, boron. So this is 5. Yeah, atomic number is 5. Z equals to 5. So if I write 1s2, 2s2, 2p, 1. Yeah. So if I say this is S, this is P, this is 1s, there will be 2 electrons here. Now if there is 2 electron here, there is 1 electron here. I'll shift 1 electron here. Okay. So this is going to have 1. This is going to have 1. So here you are getting sp2. What, children? You are going to get sp2 hybrid orbitals. Okay. And with that sp2 hybrid orbitals, fluorine will come and combine. Okay. So how it is going to combine? Let us see. So suppose you are having, this is one of your, okay. So one fluorine is going to combine. Okay. Fluorine will combine with what orbital, children? P orbital. So it is going to combine like this. One fluorine will come and combine here. One fluorine will come and combine here, and one fluorine will come. And this is for boron. This is for fluorine. Yes, so this is how your BF3 molecule will have what kind of hybridization, children? sp2 hybridization. Yes, okay. And the one thing that you need to note here, that the angle between these hybrid orbitals, okay, this is your 120 degree. So this angle is your 120 degree. Okay, 120 degree. In case of sp hybrid orbital, children, this angle will be your how much, children? This will be 180 degree. Yes, this will be 180 degree. This will be 120 degree. And we know that whenever it is sp2, the shape is planar, and when it is sp with no lone pairs, the shape is linear. The shape is linear. Okay, tell me, children, do you have any doubt till this much? Is there anything that you want to ask me till this much? Let me check. Okay, so let us continue further and move ahead. Okay, the next type of hybridization that we are going to see, children, is your sp3 hybridization. What, children? sp3 hybridization. Yeah, as you can see, this is 1s and you are having 3p. Yeah, so you are going to get 4 sp3 hybrid orbitals. You are going to get 4 sp3 hybrid orbitals. Yeah, so as you can see, this is 1s, this is p, this is p, this is p. You are going to get sp3 hybrid orbitals. And how does a sp3 hybrid orbitals look, children? It looks something like this: one above, and you can have 3 below, like this. This is your sp3 hybrid orbital. Yes, tetrahedral. Okay, tetrahedron is formed here. And the angle, children, this angle, as you can see, between this hybrid orbital is 109 degree and 109.28, right? So this is your angle. Yes, and if we take an example, tell me an example. Can I take CH4, methane? So let us see what happens in case of carbon here. So I'll write it down here. So carbon is having Z equals to 6. So we had already drawn the diagram: 1s2, 2s2, 2p2. Yes, so I'll make diagrams here. This is for S, this is for S, and this is for P in the ground state. So these are having 2. This itself is having 2 again. Okay, then what we are going to do? We are going to promote. Now we'll promote one here and one will come here. So you are going to have one here and you are going to have 3, a total of 4. Then you are going to have your 1s and you are having 3p. So you are going to get 4 sp3 hybrid orbitals. And how does it look like? It looks something like this. Okay, this is for what, children? This is for your carbon. This is for your carbon. Now hydrogen. Hydrogen is having only one orbital, that is an s orbital. So one hydrogen here, one hydrogen here, one hydrogen here, and one hydrogen here. Okay, so this is going to be the shape of, this is going to be the shape of CH4. Okay, this is your methane. So example is methane. And in case of sp3 hybrid orbital, we learned about the angle. And what is the shape, children? The shape is tetrahedral. Tetrahedral. When lone pair is equal to 0, when LP is equal to 0, your shape will be tetrahedral. Okay, is it clear, children? Let us move ahead and see. Now, sometimes what happens, children, apart from sp3, sp2 and sp, we are having other hybridization as well, which is involving d orbital. D orbitals, and let us see what happens here, and I'll give you some examples and I'll explain you. Okay, so let me read out the points, what is being written here. The from that also we are having the d orbitals, right? Then The next point, the energy of 3d orbitals are comparable to that of 3s. So 3s is nearly equal to 3p is nearly equal to 3d. That means it is telling that if they are having comparable energy, then can we mix them? Yes, we can mix them. That's why d orbitals undergoes hybridization. Yes. The energy of 3d orbitals are also comparable to 4s and 4p orbitals. So it can combine with 3s and 3p, also with 4s and 4p, because it is having comparable energy with all of them. As a consequence of the hybridization involves either 3s, 3p and 3d, or 3d, 4s and 4p is also possible. Okay, so this 3d, if you are talking about a third period, they are having s and p plus d, right? So this d, 3d can combine either with 3s, 3p plus 3d, or this thing can also combine with 4s and 4p. Okay, because this is having similar to them and this is also having similar to them. Okay, so you can have anything, and we'll see some examples here. So let us go ahead and see some examples. The first example that I'm going to talk of here is your PCl5. What, children? PCl5. The second example that we will be talking here is your SF6, but let us first talk about PCl5. So what happens in PCl5? For P, Z equals to, we know that it's 15. Yeah, Z is equal to 15. Yeah, then, so if we write down the electronic configuration, 1s2, 2s2, 2p6, 10 done. So 3s2, 3p3. Yes, 15 done. Yes, 2, 4, 10, 15. Yes. So if I write down, we know that only the last shell is going to participate in your hybridization. So this shell is going to participate in your hybridization. So now if I write down here, this is 3s, 3p. In addition, they also have 3d, which is although vacant right now, but they are having that. Yes. So if I write down now, this is having 2. Yes, this is your 3s. This is 3p. It is having 3. 1, 2, 3. Done, children. Okay, this is done like that. Now what we are having? We are having 3d here. 3d is there here. Now we want to form 5 bonds. How many bonds? 5 bonds. So what I'm going to do, I'm going to shift one of these to 3d. Okay, so that I will do hybridization. So this is here, and 1, 2, 3. This is here. So after we shift, what are we going to get? 1, 2, 3, 4, 5. Okay, so we did this, and after doing this, now what happens? Chlorine will have which orbital, children? It is also having, this is having, in the last shell, it is having how many electrons, children? It is having 5 electrons, and 1 electron will be in a p orbital, which is unpaired, right? So this is going to come and combine. This is for 1 chlorine will come here, 1 chlorine will come here, 1 chlorine will come here, and 1 chlorine will come here. So now it's going to form bonds. Yeah, this chlorine is going to give one of its electron and form bonds. This is how your hybridization takes place. And what will be the hybridization, children? This is S, this is P3 and 1D. So the hybridization will be sp3d. Hybridization will be sp3d. Yeah, okay, understood, children? So this is how your hybridization involving d orbitals is taking place. I hope you all are understanding it. Next example that we are going to see, children, is of SF6. We are going to see the hybridization for SF6. What happens in case of SF6? Your Z is equal to 16. Z is equal to 16. If Z equals to 16, let us draw the diagrams for it. 1s2, 2s2, 2p6, 3s2, 3p4. Yes, 2 plus 4, 10. Okay, 2 plus 2, 4, 6, 10, 16, right? And the last shell is this one. Okay, so we'll focus only on the last shell here. So I'll write down this in the ground state. This is P and this one is your D. Okay, this is 3D, this is 3P, and this is 4S. Sorry, 3S. Okay, so now let us fill the electrons here. 1, 2, 3, 4. Okay, so here initially we are having 2 and 1, 2, 3 and 4, and D is empty. Now in the excited state, how many electrons do we need, children? We need 6. Okay, so we are going to promote now. This one is going to go here. and this one is also going to go here. Okay, so now if I'm promoting, so this is the S, this is the P, and this one here is your D. Yeah. Okay, so now what's going to happen? This is going to have 1, 2, 3, 4, 5, 6. Yes, 6 electrons. Now it will undergo hybridization, children. Okay, this is 1s, this is 3p, okay, and this is 3d. Okay, so what will be the hybridization, children? The hybridization will be sp3d2. So hybridization is sp3d2. Yeah, now we'll bring the fluorine atoms here. Okay, let's bring the fluorine atoms here, and they are going to form bonds here. So one fluorine here. Okay, fluorine, 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 fluorine. So fluorine will give one electron, and it's going to form bonds here. As you can see, 6 bonds are being formed here. Yeah, fluorine is going to form bonds with its p orbital. Which orbital, children? With its p orbital. Yes, I hope this is clear, and the hybridization is sp3d2. Your homework is you have to tell me what is the shape in case of sp3d and sp3d2, and along with their, if lone pairs are there, then what is going to be the shape. I have already given you the table, so do refer to it. And instead of doing this, if it is asked to explain, you can do it in this way. If it is just asked you the hybridization and the shape, you can refer to the table and the trick that I told you in the previous lectures. If you haven't watched it, go and watch the trick for the previous lectures and find it out. Okay, so this is done. We are done with hybridization. So next thing that we are going to discuss, children, is your molecular orbital theory, or MOT. Okay, so MOT is basically a quantum mechanical model. And what this quantum mechanical model is describing, that how electrons are behaving in a molecule. So we are having a molecule, there also we are having electrons. So what kind of nature of these electrons, how do they behave in this molecule, that is being explained by your MOT. Okay, and in atomic orbitals, we used to see how the electrons are present in the atoms. Now here we will talk about the extended version of this atomic orbital theory, where we'll talk about the behavior of electrons in the molecules. Basically, what happens is your atomic orbitals, they combine together by the process of linear combination of atomic orbitals. They combine linearly to form your MOTs, or molecular orbitals. Okay, let us see. So MOT describes, what does it describe? The behavior. Whose behavior? The electrons in a molecule. That is the first point. Then this is an extension of which theory? Atomic orbital theory. Then what happens in MOT? Molecular orbitals are formed. How are they formed? By linear combination of atomic orbitals, or LCAO method. Okay, linear combination of atomic orbitals, they are forming your MOTs. Yes. Okay. Now, what exactly are these molecular orbitals, children? We'll see. Okay, so we know that whenever atomic orbitals combine, they form a molecular orbitals, and there the electrons are distributed. Okay, so how are MOs formed, children? They are the result of combination of atomic orbitals and describe the distribution of electrons in a molecule. Hope it is clear. Then now it is telling that molecular orbitals can be formed either by adding or subtracting AOs based on their phases. So what is this? We will be seeing this in the next diagrams. We'll understand by that. Okay, now these atomic orbitals, how are they formed, children? Either by adding or subtracting the phases of AOs. The phases of AOs. Phases, I have told you, we have one phase like plus, another phase is minus. So we'll see what happens when we add the phases and what happens if we subtract the phases. Okay, so if you are adding the phases, then you are going to get molecular orbitals. If you are subtracting the phases, you are going to get anti-bonding molecular orbitals. So there are basically two types of atomic orbitals. One is your, there are two types of molecular orbitals. One is your bonding MO, bonding molecular orbital. Another is your anti-bonding molecular orbital. This bonding molecular orbital is having an energy which is lesser than the combining atomic orbitals. This anti-bonding is having an energy higher than the combining atomic orbitals. Okay, ठीक है? क्या इतना बातें समझ में आ रहा है? जब बॉन्डिंग मॉलिक्यूलर ऑर्बिटल फॉर्म होता है तो हम लोग एटॉमिक ऑर्बिटल्स को ऐड करते हैं तो बॉन्डिंग मॉलिक्यूलर ऑर्बिटल फॉर्म होता है, और वहां पे जो एनर्जी होता है वो बॉन्डिंग मॉलिक्यूलर एनर्जी से, बॉन्डिंग मॉलिक्यूलर ऑर्बिटल से कम ही होता है। ABMO में जो एनर्जी होता है वो बॉन्डिंग मॉलिक्यूलर ऑर्बिटल से उनका एनर्जी जो है वो कम रहता है, ज्यादा रहता है। ठीक है, समझते हैं इसको, डायग्राम से हम लोग समझेंगे। सो द टाइप्स ऑफ मॉलिक्यूलर ऑर्बिटल्स वी आर गोइंग टू सी। देयर आर टू टाइप्स, वन इज योर एंटी बॉन्डिंग, वन मोर इज योर बॉन्डिंग। ओके, जैसे कि वहां पे हमारा सिग्मा और पाई होता था, यहाँ पे भी हमारा सिग्मा और पाई है। बॉन्डिंग को हम लोग सिग्मा और पाई बोलेंगे, जो एंटी बॉन्डिंग है उसको हम लोग सिग्मा स्टार एमओ एंड पाई स्टार एमओ कह के कहते हैं। स्टार लग गया तो एंटी बॉन्डिंग। ठीक है, जो इलेक्ट्रॉन्स यहाँ पे होते हैं दे कंट्रीब्यूट टुवर्ड्स स्टेबिलिटी, मॉलिक्यूल को और स्टेबल बनाते हैं, स्टेबल बनाते हैं, इसीलिए इनका जो एनर्जी है ये कम होता है तुम्हारे एटॉमिक ऑर्बिटल से। इलेक्ट्रॉन्स डिस्टेबिलाइज द मॉलिक्यूल, यहाँ पे जो इलेक्ट्रॉन्स होते हैं वो डिस्टेबिलाइज करते हैं, मतलब उनका जो एनर्जी होता है वो AO से ज्यादा होता है, वो AO से ज्यादा होता है। ठीक है, ओके, लेट्स गो अहेड। हमें पता है दैट atomic orbitals can be represented in the terms of wave function, they are represented in the forms of wave function। अगर हम दोनों को ऐड कर रहे हैं, अगर हम दोनों को ऐड कर रहे हैं, there are two atomic orbitals, one represented by psi A and other represented by psi V, when you add them you are going to get bonding molecular orbital। इसका क्या मतलब है, हमको पता है कि ये एक फेज है, ठीक है, ये ऐसा है, ये इसका क्रेस्ट, ये ट्रफ, क्रेस्ट ये ट्रफ। जब क्रेस्ट से क्रेस्ट मिल रहा है, देखो एक का क्रेस्ट ऐसा है, दूसरे का क्रेस्ट ऐसा है, तो ये इसके साथ ऐड हो रहा है, ये इसके साथ ऐड हो रहा है, तो यहाँ पे एक बड़ा सा क्रेस्ट आ रहा है, यहाँ पे एक बड़ा सा ट्रफ आ रहा है, तो ये होगा तुम्हारा बॉन्डिंग मॉलिक्यूलर ऑर्बिटल। समझ में आ रहा है बच्चा लोग? ठीक है, तो जब क्रेस्ट से क्रेस्ट मिलता है तो फेज में है वो लोग। ठीक है, कहाँ पे है वो लोग? फेज में है। ठीक है, पर अगर यहाँ पे क्रेस्ट है इसका और यहाँ पे इसका ट्रफ मिल रहा है, इसके क्रेस्ट के साथ इसका जब ट्रफ मिल रहा है वो तुम्हारा ABMO। ठीक है, समझ आ रहा है बच्चा लोग? फिर से बताती हूँ एक बारी और देखो, यहाँ पे एक मॉलिक्यूलर ऑर्बिटल, यहाँ पे एक एटॉमिक ऑर्बिटल, दोनों एटॉमिक ऑर्बिटल्स हैं। इसका देखो यहाँ पे क्रेस्ट ट्रफ क्रेस्ट ट्रफ क्रेस्ट ट्रफ, इसका भी जब हम लोग देखेंगे क्रेस्ट ट्रफ क्रेस्ट ट्रफ क्रेस्ट ट्रफ क्रेस्ट ट्रफ। ठीक है, जब ये ऐड होगा ना बच्चे लोग, इसका क्रेस्ट इसके साथ ऐड हो रहा है, देख पा रहे हो तुम लोग, तो यहाँ पे ये ऐसा कुछ फॉर्म होगा। ठीक है, समझ आ रहा है? पर जब हम लोग एंटी बॉन्डिंग देखते हैं, जब हम लोग एंटी बॉन्डिंग देखेंगे बच्चा लोग, तो वहां पे क्या होता है, देखो यहाँ पे ऐसा है, यहाँ पे एक एटॉमिक ऑर्बिटल है, तो यहाँ पे हम लोग बनाते हैं क्रेस्ट ट्रफ क्रेस्ट ट्रफ क्रेस्ट ट्रफ, पर यहाँ पे तुम्हारा क्या हो जाएगा, ट्रफ क्रेस्ट ट्रफ क्रेस्ट ट्रफ क्रेस्ट। ठीक है, तो ये वाला जो क्रेस्ट है वो ट्रफ से मिल रहा है यहाँ पे, तो यहाँ पे ये क्या हो जाएगा, ये एंटी बॉन्डिंग हो जाता है। ये क्या हो जाता है? एंटी बॉन्डिंग। जैसे कि तुम लोग यहाँ पे देख रहे हो, यहाँ पे नोड्स आ रहे हैं, यहाँ पे नोड्स, नोड्स मतलब जहाँ पे इलेक्ट्रॉन डेंसिटी जो है वो नहीं होता है, तो यहाँ पे ये एंटी बॉन्डिंग है, और ये जो तुम्हारा मॉलिक्यूल को डिस्टेबिलाइज करवाता है, डिस्टेबिलाइज करवाता है, और इसका जो एनर्जी होता है कंबाइनिंग से ज्यादा होता है, कंबाइनिंग एटॉमिक ऑर्बिटल्स जो होते हैं उससे ज्यादा होता है तुम्हारा ये वाला बॉन्डिंग। ठीक है, बोलो समझ आ रहा है बच्चा लोग? यस, आगे चलते हैं। तो बेसिकली हमको दो चीजें पता चला, अगर हम यहाँ पे बात कर रहे हैं सिग्मा एमओस का, तो एक होगा हमारा यहाँ पे जो बना है, दिस इज योर सिग्मा बॉन्डिंग मॉलिक्यूलर ऑर्बिटल, और ये जो बना है दिस इज सिग्मा एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल। जैसे कि तुमको पता चला, जब हम एटॉमिक ऑर्बिटल्स को ऐड करते हैं तो हमारा बॉन्डिंग मॉलिक्यूलर ऑर्बिटल फॉर्म होता है, जब हम उनको माइनस करते हैं, जब आउट ऑफ फेज होते हैं, तो ABMO फॉर्म होता है। ठीक है, जैसे कि यहाँ पे तुम लोग देख पा रहे हो, तो जब भी कंबाइन होगा तो हमारे दो सेट ऑफ ऑर्बिटल्स यहाँ पे फॉर्म होंगे। ओके, यहाँ पे एक नीचे फॉर्म होगा, जैसे कि देखो यहाँ पे 2p कंबाइंस कर रहे हैं, जब 2p कंबाइंस करेंगे तो यहाँ पे पाई 2p हो रहा है, और एक एंटी बॉन्डिंग जो कि पाई स्टार 2p फॉर्म हो रहा है। ठीक है, आई होप बातें क्लियर हो रहा हो। ठीक है, तो यहाँ पे जब तुम लोग रिप्रेजेंट करोगे एग्जाम में तो कुछ ऐसा दिखेगा तुम्हारा डायग्राम, डायग्राम ड्रॉ करना है। तो देखो यहाँ पे एटॉमिक ऑर्बिटल्स हैं 1s, यहाँ पे और एक एटॉमिक ऑर्बिटल है 1s, जब ये लोग कंबाइन करेंगे तो अपने से कम वाला दे सकते हैं, जो कि तुम्हारा मॉलिक्यूलर ऑर्बिटल, इसीलिए यहाँ पे इसको नीचे लिखा गया है। एनर्जी देख रहे हो यहाँ पे, नीचे जो है ऑब्वियसली कम एनर्जी, ऊपर जो है हायर एनर्जी, इसीलिए ये वाला देखो सिग्मा स्टार जो कि ऊपर है, यानी कि ये दोनों जो ये तुम्हारा सेंटर है, बैरी सेंटर, सोचो कि ये वाला तुम्हारा सेंटर है, ठीक है। यहाँ पे एनर्जी एटॉमिक ऑर्बिटल्स का है, इससे कम दिख रहा है तुमको मॉलिक्यूलर ऑर्बिटल, तो ये तुम्हारा बॉन्डिंग, और ये वाले सेंटर से ये ज्यादा एनर्जी दिख रहा है, तो ये तुम्हारा ABMO, ठीक है बच्चा लोग। तो ऐसे तुमको रिप्रेजेंट करना है, जो कम रहेगा उसको नीचे रखना है, जो ज्यादा रहेगा उसको ऊपर रखना है। क्लियर? तो अभी हम लोग जो बात करने वाले हैं बच्चा लोग, वी आर गोइंग टू टॉक अबाउट कि ये जो एंटी बॉन्डिंग और बॉन्डिंग होते हैं, तो उनका एनर्जी कुछ होता है, जैसे तुम लोग 1s 2s वैसे फिल करते थे, तो यहाँ पे भी तुम लोग फिल करने वाले हो, पर यहाँ पे थोड़ा अलग है, क्योंकि यहाँ पे एंटी बॉन्डिंग और बॉन्डिंग दोनों है, तो हमको दोनों का याद रखना पड़ेगा, ठीक है। तो जैसे कि हम लोग बात करें ऑक्सीजन, फ्लोरीन, इन सब का बारे में, किसके बारे में चलो, ऑक्सीजन फ्लोरीन, मतलब एटॉमिक नंबर 8 9 जब ऐसे आ रहा है, तो यहाँ पे जब हम लोग बात करते हैं, यहाँ पे उनका एनर्जी लेवल अलग होता है, और जब हम लोग हाइड्रोजन, हीलियम, लिथियम, बेरिलियम, इन सब का बात करते हैं, ठीक है, तो उनका थोड़ा अलग होता है। तो 8 9 वो सब जो होते हैं एटॉमिक नंबर्स वाला, उनका क्या होता है, ये तुमको याद रखना है। पहले क्या आएगा, 1s बॉन्डिंग, देन सिग्मा स्टार 1s, सिग्मा 2s, सिग्मा स्टार 2s, सिग्मा 2p, पाई 2px, पाई 2py, पाई स्टार, सिग्मा। यहाँ पे ये जो ब्रैकेट में दिया गया है बच्चे लोग, इसका ये मतलब है कि इन दोनों का एनर्जी बराबर है, यहाँ पे इन दोनों का एनर्जी बराबर है। एक बारी हम लोग रिवाइज करेंगे, सिग्मा 1s, सिग्मा स्टार 1s, सिग्मा 2s, सिग्मा स्टार 2s, फिर क्या होता है, 2pz आएगा, सिग्मा 2pz आएगा, सिग्मा 2pz के बाद क्या आएगा बच्चे लोग, पाई 2px इक्वल्स टू पाई 2py, फिर पाई स्टार 2px इक्वल्स टू पाई स्टार 2py, फिर सिग्मा स्टार 2pz, ठीक है। जब तुम्हारा दूसरा वाला आएगा, जैसे कि एटॉमिक नंबर 4 5 6, इन सब के लिए सिर्फ ये दोनों एक्सचेंज हो जाएंगे, ये यहाँ पे चला जाएगा, ये यहाँ पे चला जाएगा, बाकी सब बराबर रहेगा, ठीक है। इतना सही बात है। तो जैसे कि तुम लोग बोरॉन, कार्बन, नाइट्रोजन के लिए देखोगे, तो इनके लिए नाइट्रोजन के बाद जो लोग आएंगे बच्चे लोग, ऑक्सीजन, फ्लोरीन, इनका जो है वो उस तरह रहेगा, किस तरह रहेगा बच्चे लोग, जैसे कि तुम्हारा पहला वाला डायग्राम में मैंने तुमको दिखाया, जो पहला वाला तुमको दिखाया उस तरह रहेगा, पर जब एटॉमिक नंबर 7 तक यहाँ पे तुमको दे रहा है, तुम्हारा ऐसा रहेगा। क्या रहेगा बताया था मैंने, 1s, सिग्मा 1s, सिग्मा स्टार 1s, सिग्मा 2s, सिग्मा स्टार 2s, सिग्मा 2pz, फिर उल्टा हो जाएगा, मैंने बताया था सिग्मा 2pz रहता था, वहां पे क्या रहता था, सिग्मा 2pz रहता था। उसके बाद पाई 2px इक्वल्स टू पाई 2py, तो यहाँ पे पाई 2px इक्वल्स टू पाई 2py पहले आएगा, फिर सिग्मा 2pz रहेगा, ठीक है। फिर सिग्मा स्टार 2px इक्वल्स टू पाई स्टार 2px, सिग्मा स्टार 2pz, ये है तुम्हारा ऑर्डर, ठीक है। ऐसा कुछ दिखेगा अगर हम लोग देखें तो, ठीक है। अगर हाइड्रोजन मॉलिक्यूल का कुछ हम लोग बात करते हैं, लेट अस टॉक अबाउट हाइड्रोजन मॉलिक्यूल, एक एग्जांपल लेके बात करते हैं, H2 मॉलिक्यूल का। हाइड्रोजन का एटॉमिक नंबर 1 है, तो यहाँ पे 2 है, तो टोटल 2 इलेक्ट्रॉन्स, कितने इलेक्ट्रॉन्स बचा लोग, 2 इलेक्ट्रॉन्स। अगर हम लोग फिल करें इसका मॉलिक्यूलर ऑर्बिटल्स, अगर हम लोग फिल करें, तो पहला वाला क्या था, सिग्मा 1s, यहाँ पे 2 इलेक्ट्रॉन, 2 इलेक्ट्रॉन तो हो गए, 2 इलेक्ट्रॉन्स हो गए। तो पहला ये बॉन्डिंग है, तो यहाँ पे देख रहे हो, यहाँ पे 1s में एक है और एक 1s में एक है, तो ये दोनों मिले और सिग्मा 1s आ गया। क्या आ गया, सिग्मा 1s, ये वाला खाली रह गया। तो ये इसका मॉलिक्यूलर ऑर्बिटल डायग्राम, ये इसका मॉलिक्यूलर ऑर्बिटल डायग्राम, ठीक है। इसको ठीक से ध्यान से देखो। अभी क्या है, हम लोग बॉन्ड ऑर्डर कैलकुलेट करेंगे। क्या कैलकुलेट करेंगे बच्चे लोग, बॉन्ड ऑर्डर। बॉन्ड ऑर्डर का यहाँ पे ये बताया गया है कि जो डिफरेंस ऑफ नंबर ऑफ इलेक्ट्रॉन्स होता है, जो बॉन्डिंग इलेक्ट्रॉन्स माइनस एंटी बॉन्डिंग इलेक्ट्रॉन्स डिवाइडेड बाय 2 विल गिव यू योर बॉन्ड ऑर्डर, ठीक है। बॉन्ड ऑर्डर मतलब नंबर ऑफ बॉन्ड्स के बारे में ये बताता है, जैसे कि हम लोग पहले पढ़ चुके हैं। तो अगर हम हाइड्रोजन मॉलिक्यूल के लिए कैलकुलेट करें, हाइड्रोजन मॉलिक्यूल के लिए कैलकुलेट करें, व्हाट इज द फॉर्मूला ऑफ बॉन्ड ऑर्डर चिल्ड्रन, बॉन्ड ऑर्डर इज इक्वल टू बॉन्डिंग इलेक्ट्रॉन्स माइनस एंटी बॉन्डिंग इलेक्ट्रॉन्स डिवाइडेड बाय 2। यस, बॉन्डिंग इलेक्ट्रॉन्स यहाँ पे कितने हैं, हमने बनाया था 1s2, इतना ही था। तो ये वाला बॉन्डिंग है, तो बॉन्डिंग में देख पा रहे हो 2 इलेक्ट्रॉन है, तो 2 इलेक्ट्रॉन्स माइनस एंटी बॉन्डिंग में कुछ है क्या, -0 डिवाइडेड बाई 2, सो दिस इज 2/2 इक्वल्स टू 1। इसीलिए जब हम हाइड्रोजन लिखते हैं हम H बॉन्ड H लिखते हैं। क्या लिखते हैं बच्चा लोग, इसी वजह से हम लोग H बॉन्ड H लिखते हैं, ठीक है। समझ आ रहा है, ओके। आगे चलते हैं, अगला वाला हम लोग देखते हैं। नाउ वी आर गोइंग टू टॉक अबाउट लिथियम मॉलिक्यूल। किसके बारे में बात कर रहे हैं हम लोग? लिथियम मॉलिक्यूल के बारे में बात कर रहे हैं। सो लेट्स सी व्हाट हैपेंस इन केस ऑफ लिथियम मॉलिक्यूल। लिथियम का जो एटॉमिक नंबर होता है, हाइड्रोजन हीलियम लिथियम, सो Z इक्वल्स टू 3। टोटल इलेक्ट्रॉन्स यहाँ पे 6 हो जाएंगे, क्योंकि 2 लिथियम है यहाँ पे। कितने लिथियम है? 2 लिथियम है। अगर इसका हम लोग लिखें तो पहले क्या है बच्चा लोग? 1s में 2 रहेगा। फिर क्या होता था बच्चा लोग? 2s सिग्मा स्टार रहता था, है कि नहीं बच्चा लोग? सिग्मा स्टार यहाँ पे 1s में अगेन 2 रहेगा। फिर क्या रहता था? सिग्मा 2s में 2 रहेगा। क्या इतना क्लियर हो गया कि आगे और लिखें? आगे और क्यों लिखें? यहाँ पे 2, यहाँ पे 2, यहाँ पे 2, टोटल 6 इलेक्ट्रॉन्स हो गए। कितने इलेक्ट्रॉन्स हो गए? 6 इलेक्ट्रॉन्स हो गए। तो ये उसके हिसाब से तुम लोग मॉलिक्यूलर ऑर्बिटल डायग्राम ड्रॉ कर सकते हो। पर यहाँ पे अगर हमको कैलकुलेट करने के लिए बोले बॉन्ड ऑर्डर, क्या कैलकुलेट करने के लिए बोले बच्चा लोग? बॉन्ड ऑर्डर कैलकुलेट करने के लिए बोले। तो बॉन्ड ऑर्डर का फॉर्मूला क्या है बच्चा लोग? नंबर ऑफ इलेक्ट्रॉन्स कहाँ पे? बॉन्डिंग एमओ में, माइनस नंबर ऑफ इलेक्ट्रॉन्स एंटी बॉन्डिंग एमओ में, ठीक है, डिवाइडेड बाय 2। तुम लोग यहाँ पे कैलकुलेट कर सकते हो। देखो यहाँ पे तुम्हारा क्या है? बॉन्डिंग कितना है? 2 है यहाँ पे, और यहाँ पे 2 है, ठीक है। तो यहाँ पे 4 हो गए, 4 इलेक्ट्रॉन्स, माइनस एंटी बॉन्डिंग सिग्मा स्टार, यहाँ पे 2 इलेक्ट्रॉन है, तो -2 डिवाइडेड बाय 2। सो 4 - 2 चिल्ड्रन इज 2, डिवाइडेड बाय 2 इज 1, सो दिस इज 1, राइट। सो वी हैव Li बॉन्ड Li। इसीलिए लिथियम जब बॉन्ड बनाएगा तो लिथियम कुछ इस तरह का बॉन्ड बनाएगा, ठीक है। ऐसा तो लिथियम मेटल है, वो जनरली आयनिक बॉन्ड करना प्रेफर करता है, पर इसका जो बॉन्ड ऑर्डर तुम लोग निकालोगे तो 1 आएगा। क्या आएगा बच्चा लोग? 1 आएगा, ठीक है। तो बाकी जो सब कुछ है हम लोग नेक्स्ट क्लास में डिस्कस करेंगे। कुछ और मॉलिक्यूल्स का एमओ हम लोग स्टडी करेंगे, और कुछ बॉन्ड ऑर्डर और कुछ हम लोग देखेंगे। देन वी आर ऑल्सो गोइंग टू सी योर मैग्नेटिज्म हम लोग देखेंगे, और कुछ ट्रिक्स मैं बताऊंगी तुम लोगों को, ठीक है। दैट इज व्हाट वी आर गोइंग टू डिस्कस इन द नेक्स्ट क्लास चिल्ड्रन। सो अंटिल देन टेक केयर चिल्ड्रन, बाय बाय एंड प्रिपेयर वेल।